It's my pleasure now to introduce Chen Zhang, who's a PhD candidate in computational neuroscience at the University of Southern California, advised by Professor Laurent Itti. She received her master's degree in computer science, also from USC, and her bachelor's degree in biomedical engineering from Tsinghua University. Her research interests lie in human vision, computer vision, and machine learning, focusing on theory and applications for both normal and neurological conditions. And today she's going to be talking about machine learning-based screening for fetal alcohol syndrome disorder. So, thank you.
Good afternoon, everyone, and thank you for the introduction, and thank you for having me here to present my work. We just heard two exciting applications, AI applications in the area of human health, and there are many other machine learning applications in the healthcare area. For example, the deep learning-based medical imaging analysis. Many of these applications happen at clinics or afterwards, so what about something earlier? Today I'm going to talk about a machine learning-based screening procedure for a fetal alcohol spectrum disorder. That's one type of neurodevelopmental disorder. So FASD is caused by prenatal alcohol exposure. It's one of the most prevalent neurodevelopmental disorders in North America, and almost the top one in South Africa. Children with FASD show growth retardation and impairments in the central nervous system. A severe subtype can show special facial features. FASD can place high psychological pressures and large economic burdens in areas of healthcare, social service, special education, which can cost billions of dollars annually in the United States. Early screening and detection is of significant importance because it can lead to early intervention and treatment to mitigate the severity and prevent developing secondary comorbidities or disabilities. It is crucial for neurodevelopmental disorder, especially for FASD, because there's no cure for FASD. The only thing we can do is early detection and early intervention. However, currently there's no efficient and widely used screening tools. The clinical diagnostic process can be time and cost-consuming. A large portion of at-risk population cannot have timely diagnosis because of limited clinical capacity. Different clinics can have varied diagnostic criteria, leading to inconsistency of treatment. FASD also has high comorbidities with other neurodevelopmental disorders, which can lead to misdiagnosis. So, a screening tool that is time and cost efficient, has objective and unified standards, and can be easily accessed and popularized is desperately needed. So here we're trying to propose a machine learning screening procedure that can meet with all of these challenges and may have substantial impact of the referral system and the diagnostic process. So the first question to ask is what kind of test we want to use. Given the fact that the FASD can impair structural, cognitive, and behavioral aspects of the human, so we started from a multi-modal perspective. We used 6 tests in the domains of eye movement control, psychometric tests, and neuroimaging. So the first 3 tests are called saccadic eye movement test. A saccade is a rapid eye movement where you redirect your fovea to a visual target. The first test is called pro-saccade test, where you just direct your fovea to a target. And we derive the measurements from this test, the accuracy, your performance accuracy, the variability, the main sequence, that's about the velocity and amplitude, and other sensory motor functions such as the reaction time. A second test is called anti-saccade. So instead of directing your saccade toward the target, you direct it away from the target. So besides the parameters I just mentioned, there's another measurement called response inhibition, because you need to inhibit your automatic process to the visual target. The third test is called memory-guided test. The participant need to remember the 2 targets in sequence, and then they need to direct the saccade to the correct locations in the correct order. So working memory is also involved in this test. The next test is for free viewing. So the subject is just asked to freely view. Oh, where's my mouse? I'm sorry. How can I play the videos? Cannot find my mouse. So the participant just asked to freely watch a video, and we have a camera on top of the screen to record their eye movements. Oh yeah, it works, cool. So from the right of the screen, we can see a lot of dots. That's the eye positions of the subject recorded. This test is about your visual attention. So you can direct the saccade to some interesting object. We call them a saliency object. You can also direct your saccade in a top-down manner. It's about like top-down attentional modulation. So the saliency object can have different salient aspect. We call them saliency channels. It can be color, can be orientation, can be the motion. So we computed like the saliency maps along different channels and extract your eye traces along these maps and to result in a attentional traces. So these attentional traces will be used for later analysis. The fifth test is about psychometrics. So we examine the cognitive and executive functions in areas of attention, memory, and academic abilities. The last test is about the neuroimaging. We use different tensor imaging to image the corpus callosum. That's a part in the middle of your brain connecting the two hemispheres. We recruited relatively large clinical group, and also it's age-matched typically developing controls. And we have 22 FASD and 24 controls computed all of the 6 tests. That's a large experimental setting. The next step is about the classification. For a lot of the measurements we derived from the test except the free viewing because the data are relatively low dimensional. So we use the SVM-based procedure called recursive feature elimination. It's an iterative procedure, and at each iteration will delete the least useful feature. So after termination, we can have a basic classifier together with its corresponding feature groups. We do the feature selection and classification at the same time. For the free viewing data, we first compute the saliency map and extract their attentional traces, as I mentioned before, and then we pass the attentional traces through a convolutional neural networks. Because we have different video clips, we'll have different learned representations for the attentional traces. Then we have another layer of classifier to do the video selection and the final prediction. And after that, we did another multi-modal analysis for the group of the subject who finished all of them. We trained a classifier from the outcomes of the single classifier. The final classifier can be whatever type you want. Here we use a logistic regression because it's easy to train and easy to generalize. So for the during the classification procedure, we also discovered the most distinguishing features related to the disorder to get a profile, comprehensive profile, I should say, of their neurocognitive or neurobehavioral impairments. And we can get a better accuracy if we do a multi-modal analysis. And this accuracy, about 85%, is comparable to the state of art for other screening procedures. But most of the other screening procedures use the similar measurements as what the clinicians use. And the further analysis show that only using pro-saccade, anti-saccade, and free viewing and psychometric can result in that accuracy. Besides the accuracy, you can also evaluate the test from different aspects, such as the time, its restriction, cost, and accessibility. The free viewing and the pro-saccade use the list of the time, has a list restriction and cost list, and is easy to access. So we propose a screening procedure here, so we just use the pro-saccade and the free viewing framework. And if the participant meets its requirement, we can add another anti-saccade with no extra cost. And if we need to pay more attention, more time or money, we can do 3 subtests from the psychometrics. And such a procedure can provide the quantitative and objective signature of the disorder from their cognitive and executive function areas. And the data can be analyzed through the same machine learning pipeline with unified standards and much easier to be implemented with early and preschool age children. To quantify the monetary benefits, we derive a model from the theory of value of information. So the CS denotes the cost of the screening. For the correct detection, there's a rate of detection rate. PF refers to the fraction of patients, and Y minus PF refers to the fraction of control. If we have a false alarm, if we classify control as FSD, and true negative if the control is control, and the missing rate if we miss one patient. And there's a gain of G that can be denoted for if we correctly detect a FSD because we lead to early intervention. There's a cost for the clinical diagnosis, and there's a loss if we miss one patient. And the expected value can be calculated at the sum of the probabilities times the outcomes. And for an individual case with FSD, if we do the ProSACAD and the free-viewing screening annually, the expected saving can be over $7,000. If we extrapolate this calculation to our 46 participant group, and if we do the full set of the screening, that's the pro and anti-SACAD, free-viewing, and psychometrics, the expected saving annually can be as high as over $187,000. So to conclude, our machine learning based screening procedure is high throughput and low cost. It can be widely used, target at the at-risk population, accelerate the clinical process, and lead to earlier interventions and treatment, which is crucial to neurodevelopmental disorders. I'd lastly want to acknowledge my collaborators, Angelina, James, and Doc from Queen's University here in Canada, and Paul He, who is a former lab member, and my advisor, Laurent Itti, and also our founders. And thank you, and I'm open to questions.
Thank you. Thank you. Any questions?
Thank you for your time and your attention.